Let's talk about degree sequence in a graph. Degree sequence is a nothing but it's an integer sequence, which is generally in non-decreasing order. Example, let me take this graph A, B, C and D. For this graph, degree sequence is writing integer sequence of degrees in non-decreasing order. First, let me list out all the degrees 1, 3, 2 and 2. Okay, so if I write them in non-decreasing order, it will be 1, 2 and 2 and 3. This is called degree sequence. So in that way, for every graph I can write degree sequence, isn't it? Yes. So now the question is, which is interesting, given a graph degree sequence, can we have a graph? That's a question, reverse question. So this direction is easy. That means given a graph, do we have a degree sequence? Yes, that is always. But given an integer sequence, which is in non-decreasing order or anything, for that can we have a corresponding graph? So sometimes it may not be possible. Example, let me take 1, 1, 1. So with this 1, 1, 1, no one can draw graph. Not only simple graph. So any graph, even I can't draw multigraphs with loops too. Okay, the reason is sum of the degrees theorem. Every graph should satisfy sum of the degrees theorem. Then really this degree sequence has a graph. Let's assume that there is a graph and let's say we can draw it. Then according to the sum of the degrees theorem, the sum of the degrees of this graph should be even number, right? Because 2 into e. But since we know that the degree should be 1, 1, 1, then here sum of the degrees is odd, then you can't draw the graph. If you draw the graph, sum of the degrees should be even. Then I can't prove that sum of the degrees is even for this degree sequence. So there should not be any graph with this. Understand? Now, let's say sum of the degrees is even. Okay, like 1, 1, 2, 2. Now, is there any graph with this corresponding sequence is a question. So for that, what I do is first I do trial and error method. Okay, let me do trial and error method. A, B, C, D, right? I'll take A, it's degree 1. Let me do it. Okay. Then I will take, one more vertex B and its degree also 1. I draw like this. Okay. Now I need two more points. Let's say it is C and D. Their degree should be 2, 2, but effectively at this moment, degree of C is 1, degree of D is 1. Isn't it? Then by adding one more edge like this, probably you can get it, right? 2, 2, 1, 1. Yes. So that means, so using trial and error, I realize that this sequence has a graph. But the question is, can we always guarantee whether there is a graph or not? That's a question. Okay. Now let me put that question in simple words. Given an integer sequence, can we say whether there is a graph for that integer sequence or not? That's a question. For that, answer is, let's say if it is any graph, then always graph is possible. If the question is there any graph, then yes, always it is possible, but sum of the degrees of sum of that integer should be even number. We know that if sum of the integers is odd, we can't draw the graph. We know that. But what if some of the integers are even? Do we always have graph? Absolutely. Okay. I will show you a method to construct such graph. Example, let's say you have 2, 2, 4, 4, 5, 5. Okay. Why there is a graph with this integer sequence, I will tell you. Let me denote them with A, B, C, D, E, F. Follow this method. That method always gives you such graph. Okay. So for that what you do is divide your integers into two parts. The numbers which are greater than or equal to 2, the numbers which are less than or equal to less than 2. Greater than or equal to 2 means 2, 3, 4 so on. Less than 2 means 1 or 0, isn't it? So whenever a number is greater than or equal to 2, then remove lot of 2's from it until that number becomes 0 or 1. Example, let's say 4, right? Remove 2, then it will become 2 and again you remove one more 2 in that way. So remove some 2's so that effectively the resulting number should become 0 or 1. Yes, obviously when you do that, repetitively if you remove 2, 2, 2 so on, Definitely every number will become either 0 or 1, isn't it? Even numbers will become zeros, odd numbers will become 1. Let's see that. 4 minus 2 minus 2, 0. 5 minus 2, 2, 3. 3 minus 2, 1, right? So here 5 minus 2, 3. 3 minus 2, 1. In that way. So 2 minus 2, 0. And 2 minus 2, 0. Understand? So in that way, so I will tell you the reason why I am removing, this is 1. This is 1. I will tell you the reason why I am removing 2's. Okay. So finally, you get zeros and ones. One interesting question here is, please stop this video and think about it. How many zeros you get? How many ones you get? Okay. Since even numbers gives you zeros, odd number gives you ones, then it depends on the number of even numbers and number of odd numbers you have, right? And in any graph, so each odd number represents odd degree, isn't it? But we know the theorem that number of odd degree vertices in any graph is even, right? Number of odd degree vertices is even. You remember that fact. Since only odd numbers gives you ones, if in this process, then I can say that number of odd degree vertices are, so number of ones in the resultant set, in resultant sequence is equal to even number. Remember it, okay? So what I am going to do is, once this process is over, so for every removal of 2, I construct like this. I draw a self loop in the graph. First I take initially all the vertices like A, B, C, D, E, F. Okay. Now for A, you removed 1, 2, right? For that, here to balance that act, I draw self loop. For B, to make degree 0, that means we have to add one self loop. That indicates that A doesn't need any more edges, because its degree was 2 and I added it. So similarly for B, similarly for C, we have to remove 2 2's. Okay. So that degree of entire C is represented in that way. So I am representing every vertex degree here. Degree of D is 2 2's, right? That's why 2 self loops. So E, 2 self loops. Okay, this is one process. Okay, there can be another method. I am not saying that there is no other method, but this is one of the method which always constructs a graph. So F, draw 2 self loops. Now effectively, so your remaining integer sequence is 0. That means A doesn't require anything, B doesn't require any H, C doesn't require any H. In that way, A, B, C, and D is what? 0, and E is 1, F is 1. Since we know that these are all corresponds to even degrees and these are all corresponds to odd degrees, then the number of ones, it represents number of odd degrees, but number of odd degrees in any graph is even number. Then what you do is, so there are even number of ones, then we can pair them up. That means whenever you have 2 degree 1 vertices like x comma y, if you add an edge between them, then I can represent that degree 1, right? So in that way, if you have 4 degree 1s like this, then let me take x, y, w and z, draw one more edge between w and z. In that way, by pairing that even number of vertices, we can draw edges between them. So what I do is, here E comma F are such degree 1 vertices. Between them, if you add that edge, then effectively the remaining degree we are representing like degree 1. So remaining 4 degrees already represented, remaining 4 degrees already represented. Understand? So now see, this is a graph for this degree sequence. In that way, any graph can be constructed, isn't it? We never get a situation where you can't construct the graph, right? So this is about given integer sequence, if that sum of the integers is even, can we have always graph? Yes, we can, and this is a method. But there is one more problem, that is, given a graph, can we have a simple graph? Here you are using loops and all, right? Then if you have a integer sequence and the question is, do we have a simple graph for that? Is not so easy question. Okay, for that we need some theorem. Okay, now we'll answer this question. Given a integer sequence like d1, d2, d3, so on dn, can we have a graph for it, simple graph this time? Okay, we know that always we can have a graph if the integer sequence sum is even, right? We know that. Now this new question is, given this integer sequence, is there any simple graph? For that, so there is a result called Havel-Hakimi's result. Okay, let's read it. there is a simple graph for this degree sequence d1 to dn if and only if d1 dash, d2 dash, d3 dash, so on dn minus 1 dash has a simple graph. So it's a conditional thing, right? That means given our let's say imagine that this is your problem. Okay, this is new problem. We have to create a new problem. So d1 dash, d2 dash, everything is a new construction. This is our construction d1 to dn already existing. So someone asks you whether d1, d2, d3, so on dn is it has a graph or not, which is simple graph. Then you construct d1 dash, d2 dash, d3 dash, so on dn minus 1 dash, and the result says that if this graph, our original problem has a graph if and only if this newly constructed problem has a graph. But some of the students have this question. Our problem is checking whether that has a graph or not. Again, if I construct a new problem and if I check whether this construction has a simple graph or not, if I can do that, why can't I apply that to directly this one? Why I have to depend on this one? Both are same problems, right? I cannot solve, so I'm afraid I cannot solve this problem. That's why I'm thinking about that. Then why I have to use a new problem? So both are similar problems. So how can we solve this new problem now? That's what students question. So what I say is, if you observe the difference between these two, this is an integer sequence of n, n integers. This is a sequence of n minus 1 integers. That means we are reducing the problem. If you don't know whether this integer sequence has a graph or not, again you reconstruct this one. That means use Havel-Hakimi theorem one more time. Then what happens? You will form a new integer sequence with lesser lesser size than the previous one. Example, initially if your problem has integer sequence 5, then we are constructing new integer sequence up to dn minus 1. So n value 5, then dn minus 1 will become 4. Then you will be asking this question, is this integer sequence of length 4 is has a simple graph? Then if you don't know, then again you construct this back. So according to Havel-Hakimi result, so any degree sequence of length 4 is graphic. We say graphic means it has a graph. Okay, integer sequence is graphic means it has a graph. Then this integer sequence is graphic if and only if the to be constructed new sequence of length 3 is graphic. So if you use Havel-Hakimi again, then you can reduce this problem to 2, then 2 will be reduced to 1, 1 will be reduced to 0. What's the advantage of that? This is unknown. If this is unknown, again construct it. In that way, one day you will reach to a point where the number of vertices or number of integers in the sequence is 0 or 1. For such problems, always solution, isn't it? Let's try that. Okay, but how to construct this integer sequence? We'll see. The new integer sequence, let's say d1 dash, d2 dash, d3 dash up to dn minus 1 dash. Then where is dn? For dn there is no corresponding integer. Only we have integers for d1, d2 up to dn minus 1. Okay. How this d1 dash should be constructed, I will tell you. Any di dash is di, simply di. For index I value 1 to n minus dn minus 1. So di dash equal to di minus 1 for I equal to n minus dn to n minus 1. So it is depending on dn, you see, your index. Whether your di dash is di or di minus 1 is depending on I value. Let's I value, but I value is depending on dn. So what is dn? We'll see. dn is the last degree, but we know that these are all in ascending order or non-decreasing order. Then dn definitely should be maximum degree. So that means in your integers, take the maximum number and apply this operation I equal to 1 to n minus dn minus 1. Example, dn value is 5. Okay, n value is 7, let's say. Then I equal to 1, 2. I am just taking one example. So n value, let's say 7 minus 5 minus 1. 7 minus 5, 2, 2 minus 1, 1. That means I equal to 1 to 1. Okay, so for I equal to 1 to 1, di dash equal to di. That means for I value 1, d1 dash is d1. What about this one? I equal to n minus dn, where n is 7, 5, this dn is 5, 7 minus 5, 2 to n minus 1, 6. That means up to 2 to 6. di dash is just previous di minus 1. In that way you can construct di dash for every every I, correct or not? D1 dash, D2 dash, D3 dash, so on, Dn minus 1 dash. Once you do it, then check whether that is graphic or not. Already I told you what is graphic. An integer sequence is graphic if it has a graph. Okay. So if you are not sure, again we apply the Havel-Hakimi result. Okay. Let's try to use this result with some integer sequence. Let me take some random integer sequence here, that is 1, 1, 2, 2. Okay. So according to the theorem, this is graphic if and only if this construction, newly constructed integer sequence is graphic. What is that newly constructed degree sequence? We have to apply this one, di dash equal to, di, sometimes di dash equal to di minus 1, correct? Okay. From identify first what is dn in this one. This is d1, d2, d3, d4, isn't it? So d4 is 2, remember, highest value is 2. What is n here? N is 4. Apply this operation. So di dash equal to di for I equal to 1 to n minus dn minus 1. I am applying that values. N value 4 minus dn is 2 minus 1. 4 minus 2, 2, 2 minus 1, 1. That means I equal to 1 to 1. So remember this is 1 to 1. What about this one? di dash. Di dash is di minus 1 for I equal to n minus dn to n minus 1. I equal to n minus dn. N is 4 minus dn is 2 to n minus 1, 3. Right? So 2 to 3. So 2 to 3 di dash is just 1 less than di. Okay. So di dash I am writing now. Let me apply that. So for I equal to 1 to 1, first 1, I value 1, di dash equal to di. That means d1 dash is d1. So d1 dash is d1, 1. Next, from I value 2 to, this is I value, right? I value 1, 2, 3, 4. I value 2 to 3, that means 2 to 3. So di dash equal to di minus 1. These are all di's. Di minus 1. 1 minus 1, 0. 2 minus 1, 1, in that way. So what about this one? There is no corresponding, integer for this integer. Understand? You get 1, 0, 1. Now this is a process. So let me tell you this process in simple words rather than doing this model. Once you understand this concept, then the easy technique is, what this Havel-Hakimi result finally says that take the highest number, since it is 2, mark 2 integers from right to left. Why 2? Because of this 2. If this is 7, right to left, select 7 positions and mark them, from where we have to remove 1. From other points we should not remove anything. They should be previous values. Okay, that is what I am doing now. So since this value is 2, identify 2 positions from right to left and mark them, and so I am going to remove 1 from it. So this 1 is as it is because it is not marked. Since it is marked, then remove 1, 1 minus 1, 0. Since it is marked, remove 1 from it, then you get 1, 0, 1. Then the question, is this integer sequence graphic? Okay, if you don't know, then again you ask same question to Havel-Hakimi. Then according to Havel-Hakimi result, to apply that, first we have to take the degree sequence. So never take non-degree sequence. This is not a degree sequence. Generally degree sequence should be in dash form, 0, 1, 1. Okay, now the question is, 0, 1, 1 is graphic if and only if a newly constructed integer sequence is graphic, isn't it? How to construct new integer sequence? Take the maximum value, which is 1. Since it is 1, locate one point from right to left and do the operation. What is that? 0, as it is. Now 1, 1 minus 1, 0. Whenever I point it like this, then we have to remove 1 from it. Then you get 0, 0. Now you see. So 0, 1, 1 is graphic if and only if 0, 0 is graphic. But we know that 0, 0 is graphic. How? It is empty graph. You know the definition of empty graph? Empty graph is a graph with vertices, some vertices and 0 edges. So see, when you have two integers, 2 degrees 0, 0 for any graph, then we can construct it, correct? And an example, take 2 vertices AB, don't keep any edge, then it will become this kind of degree sequence, right? So that means this is graphic then this should be graphic. If this is graphic, then this should be graphic. That is what if and only if means. Then if this is graphic, this should be graphic. In that way, so we can check whether an integer sequence is graphic or not. Understand? So finally 1 1 2 2 is a this has a simple graph. Let's try to apply Havel-Hakimi result to integer sequences. But before that, we know that sum of the degrees is even number, then only there will be a simple graph, right? So for that, let me apply sum of the degrees first. 2 plus 2, 4, 7, 10, 14, 18, 23. Sum of the integers is odd number here. Then definitely, this sequence cannot have graph. Let's take second one. 1, 1, 2 to 1 plus 1, 2, 4, 6, 9, 12, 15, 19, 24. Yes, this is a valid sequence. That means this might have a graph. I'm talking about simple graph. If the question is general graph, yes, definitely this graph has this integer sequence has a graph. But the question is whether there is a simple graph or not. Then we have to apply Havel-Hakimi result. Okay, identify. Let me do it. First, if and only if a new integer sequence is graphic. So to form a new integer sequence, select the maximum degree 5, then identify 5 points 1, 2, 3, 4, 5. Remove 1 from each. Then you get 1, 1, 2, 1, 2, 2, 2, 3. Isn't it? So again, I am not sure whether this is graphic or not. Then again ask this question to Havel-Hakimi. For that, we have to submit integer sequence in increasing order, isn't it? So that's why it should be 1, 1, 1, 1, 2, 3, 4 2s followed by 3. Okay. So this is graphic if and only if identify the maximum degree 3, locate 3 points from right to left and remove 1 from each. Then you get 1, 1, 1, 2 as it is, but 2 is marked, then 2 minus 1, 1, 2 minus 1, 1, 2 minus 1, 1. Again, if you don't know whether it is graphic or not, again you convert into degree sequence first. It will become 1, 1, 1, 1, 1, 1, 2. So is it graphic? It is graphic if and only if identify the maximum degree, then locate 2 points, then again do the same operation 1, 1, 1, 1, 0, 0. Isn't it? So now this is graphic if and only if, let me construct degree sequence 0 0 1 1 1 1. So this is graphic if and only if, again same story, right? So before that, I want to tell you one thing. You can apply this process for any number of times until you get zero number of vertices, right? So that's the usual procedure. But what I want to say is, so rather than wasting the time, here I know that there is a graph like this. Whenever you know that there is a graph with this any integer sequence in between, stop it. Example, here I know that there is a graph. What is that? Degree 0, degree 0. Let me take vertex A, vertex B. Don't draw any edge for it. Then degree 0 can be represented. Next, C, D, E, F with degree 1, degree 1, degree 1, degree 1. Then I can do like this. C, D, E, F. So C to D add an edge, E to F add an edge. Yes, there is a graph for it. Then definitely there will be a graph for this one, 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 for this one. In that way, so we can prove whether a integer sequence is graphic or not. Okay. Let's talk about connectivity. So connectivity is very important topic in graph theory. So we try to understand connectivity in very in-depth way. First I start with basics. So finally what we are going to do is we are understanding here what is path, and what is connected graph, what is disconnected graph, and what are the properties of connected graph and disconnected graph. Okay. So that's the overall idea about connectivity. To understand that connectivity clearly, first we start with a formal definition called path. Okay. So what is path? Path is a simply sequence of edges, just sequence of edges. Example, see this one, 1 comma 2, 2 comma 3. What is the meaning of sequence is, if you take any edge in the path, okay, path is a collection of edges, I can say. So this is, let's say, one edge, right, 1 comma 2, and since it is ending with 2, the next edge should start with 2, then we say it's sequence. Okay, now 1 2 2 3 3 4, see, ending of one edge should be starting of another edge. In that way, if you form some collection of edges, so that is called sequence of edges. So path is collection of such sequence of edges. Okay. So we say that 1 is the starting vertex of that path, and here 3 is the ending vertex of the path. So we also represent this idea like this, so that it will be easy to understand 1 2. So rather than set form, I can take this kind of picture like this one, pictorial representation 1 to 2, then 2 to 3, and this one 3 to 4, and next one starts with 4 and ends with 3. So I can write like this also, 1 2 3 4 3. Starting vertex is 1, ending vertex is 3. Number of edges in this path is 1 2 3 4, and this is a path. Okay, but what is not path is this one, 1 to 2 5 to 6. This is not a path because it should be sequence of edges. Okay, there is one interesting path, that is trivial path. That means if I start at 1 but I don't take any number of edges, that means I take 0 edges, then still we say that is a path. So this is a path. Okay, so you are not seeing any path here, right? So you are just seeing a vertex. Yes, you can't see path clearly because there is no edge inside it. So this is called trivial path. Okay, trivial path. Trivial path is a path with 0 edges. Okay, then how to imagine this path I will tell you. Let's say Raju is an imaginary student. Okay, Mr. Raju is starting at city 1, like he want to go from, let's say city 1 is Hyderabad. Okay, so Raju want to go from Hyderabad to Hyderabad without any cost, like without any road. Then what he can do is, so he will start at Hyderabad, let's say 1, then he will close his eyes and he will open his eyes. That's it. Then he will be at Hyderabad. So that path is called trivial path. So every vertex, by starting at any vertex, always I can have a trivial path, right? So this is about trivial path. But don't get confused with loop. Example, if you have loop like this, that is different. Example, Raju starts at 5, and if he uses loop, then he will use one edge. Then pictorially we represent like this. This is not trivial path because this path contains one edge, right? So if there is any path without any edges, that is called trivial path. So that's why self loop is, if you take self loop in the path, that is not trivial path. Okay, so it's also non-trivial path. Now this is about paths. Let's come to simple path. What is simple path? So simple path is a path, what is path? Without repetition of edges. Okay, we should not repeat the edges. Example, here 1 to 2, 2 to 3, 3 to 4, 4 to 3. You see 3 to 4, 4 to 3 is same edge, isn't it? So you have repeated an edge here, then this is not a simple path. Let's draw one simple path here. Example, 1 to 2, then 2 to 5, 5 to 6, 6 to 3, 3 to 4, 4 to 1. This is a simple path, right? So here starting vertex equal to ending vertex. So what? Still the question is about, it should be a path. The definition says that we should not have repetition of edges, right? Are we repeating edges is the question. This is 1 to 2 edge, 2 to 5, 5 to 6, 6 to 3, 3 to 4, 4 to 1. No repetition of edges. Some students say that, sir, you are repeating here. I am repeating vertices, not edges, isn't it? Don't get confused between vertices and edges. Okay, that's why still this is a simple path. Okay, you can have a lot of such paths. Every trivial path, example, so 1 is a trivial path, isn't it, with 0 edges. This is a simple path because you are not repeating edges. Even you are not repeating edges, you don't have edges, then definitely every trivial path will become simple path. Okay, now let's see closed path. So closed path is a path, what is path? Where start vertex equal to end vertex. So simple. Example, let's take this graph. 1, 2, 3, 4, 5, 6. In this one, closed path is nothing but 1 to 2 and 2 to 3, 3 to 4, 4 to 1. Already we know that it's a path, and just observe starting vertex and ending vertex. Both are same, isn't it? That's why it's a closed path. One more example, 1 to 2, 2 to 1. Yes, I am repeating the edges. That's not an issue because in a path you can repeat the edges, isn't it? So in simple path you can't repeat the edges, but in general path we can repeat the edges. not a issue, and starting vertex equal to ending vertex. That's why these are all paths where starting vertex equal to ending vertex. So closed paths. Now open path. Open path is a path like any path where start vertex not equal to end vertex. That means starting and ending is different. Example, let's take 1 to 2, 2 to 3, 3 to 4, 4 to 1, which is closed path. Let me add one more edge, 1 to 2. See, this is not closed path. The reason, it's a path but where starting vertex not equal to ending vertex, isn't it? But for closed path, start should be equal to ending. That's why it is open path. I can say that open path is a path which is not closed. Okay. Now you understand what is open path, what is closed path. So in closed path, starting equal to ending, and in open path, starting not equal to ending. Now we'll see circuit. So let me read the definition of circuit. Circuit is a simple closed path. You know what is path? You know what is closed path? Where starting vertex equal to ending vertex. One extra condition is simple. So what is simple path? Simple path is a path without repetition of edges. Let's consolidate all of these things. One, it's a path where starting equal to ending, and simple means no repetition of edges. Any path without repetition of edges and which is closed is circuit. An example, let me take this one. 1 to 2, 2 to 3, 3 to 6, 6 to 5, 5 to 1, and 1 to 4, and 4 to, let's take 1 back. This is circuit or not? We'll see. First thing, let me check the definition. In definition, first it should be path. Yes, it is a path. Already I checked it. You also check it. Next, is it closed path? Yes, starting equal to ending. But is it simple? If it is simple, no repetition of edges. But you see here, 1 to 4, 4 to 1. I have repeated the edges. That's why it is not circuit. In that way, easily we can check whether a path is circuit or not, isn't it? Let's see one more example of graph. Let me take a graph 1 to 2, 2 to 3, 3 to 4, and 4 to 5, 5 to 6, 6 to 4. Let me put an edge here, here to here, and here to here, here to here. So my question is, I'll give you a path and check whether it is simple closed path or not. Otherwise, is it circuit or not is a question. I'll give you a path. 5 to 1, okay, 5 to 1, 1 to 2, and 2 to 4, and 4 to 1, and 1 to 5, then 5 to 6, and 6 to 4, 4 to 5. I have given some path. Is it circuit is the question. We'll see. First step, it is really circuit, simple closed path. That means it should be closed path where starting should be equal to ending. Perfect. 5 equal to 5. Second one, what about simpleness? Is it a simple path? Then there should not be repetition of edges. Let me mark the edges in this graph so that I can check the repetition. 5 to 1. Yes, let me cover it. 1 to 2. Yes. 2 to 4. 2 to 4. Okay, this is covered. 4 to 1. Okay. 1 to 5. See, you have repeated 1 to 5 two times. That's why even that path is not circuit. Okay. One more example. Let's take 5 to 1, 1 to 4, 4 to 2, 2 to 3, 3 to 1, 1 to 6, 6 to 5. Is it a circuit? Is the next question. Stop the video here and think about it, whether it is circuit or not. Okay. After that, after solving this problem, again start the video. Okay. Start. 5, 1, 4, 2, 3, 1, 6, 5. Is it a simple path? We will see. For that, no repetition of edges. 5, 1, 1, 4, 4, 2, 2, 3, 3, 1, 1, 6, 6, 5. I don't see any repetition of edges. That's why it is a simple path. And is it closed? Yes, starting equal to ending. Okay. So that's why it is circuit. Simple closed path. In that way you can understand about circuit. We'll see one more thing, which is cycle. So what is cycle? Cycle is a circuit. Okay, you know what is circuit. But extra condition. What is it? Where no repetition of vertices. We should not repeat the vertices. But without repetition of vertices, how can you form closed path? And why should we form closed path first of all? To form circuit, it should be closed path. But cycle says that its condition is circuit and where no repetition of vertices. Without repetition of vertices, how can you form the closed path? That's why the exception at the end you can repeat the vertices at the end, you can repeat, that's possible. Apart from that, you should not repeat the vertices. Okay, that's the exception. So finally, cycle is a circuit where no repetition of vertices except last vertex and first vertex. So example, is this path a cycle? If really it is a cycle, then what is the condition? First of all, it should be circuit. Yes, we know that it is circuit. And what is the extra condition? No repetition of vertices. Okay, don't check this one because without that we can't form a circuit. Apart from that, you can see the repetition of vertices here, isn't it? That's why it is not cycle. One more example I will show you. 5 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 6, 6 to 5. Is it a cycle? We'll check. Blindly follow the definition. What is the definition of cycle? First it should be circuit. What is circuit? Go to the definition of circuit. Simple closed path. Okay, first of all let me check whether it is circuit or not, then after that I will check whether it is cycle or not. Okay, so circuit, simple closed path, simple, no repetition of edges. 5 1 1 2 2 3 3 4 4 6 6 5, no repetition of edges. Okay, if you have any doubt, go to the graph and mark the edges. Based on that you can decide whether edges are repeated or not in the problem. Second one, yes, no repetition of edges. Is it closed? Yes, 5 and 5. Yes, simple closed path. So that's why this is circuit. But a circuit is cycle only if there is no repetition of vertices. So apart from these ends, are you seeing any repetition? No, right? That's why no repetition of vertices. It is a cycle. So these are all fundamental things in connectivity topic. Okay. So you learn what is path, what is simple path, what is closed path, what is open path, what is circuit, what is cycle, isn't it? So using that we are going to define connectivity. We'll see some more terminology of graphs, that is subgraph and spanning subgraph and induced subgraph. We'll see one by one. So what is subgraph of any graph G V comma E? I have a graph G V comma E. Then what is subgraph? So subgraph, let's denote it by G dash and vertices, let's say V dash, edges E dash. I am defining subgraph of G V comma E, where vertices are V, edges are E. Then according to the definition of subgraph, it is like this. V dash, your new vertex set, should be subset or equal to V. Second one, the edge set E dash should be subset or equal to E. Then you will form subgraph of given graph. So simply vertex set you take which is subset of V and edge set you take which is subset of E. Example, let me take a graph 1 to 2, 2 to 3, 3 to 4, 4 to 1. For this graph G, let's say G dash which is subgraph. For that what I have to do? I have to take some subset of vertices, any subset. What if I take all the vertices? Still not a problem. Let me take all the vertices 1, 2, 3, 4. One more possibility, let me take G double dash. So take a few vertices, like anything randomly, 1, 3, 4. Anything is possible. Then take subset of edges. So you have edges 1 to 2, 2 to 3, 3 to 4, 1 to 4. Let me take subset like this 1, 2. I have taken some subset of these edges, right? That's why this is subgraph. Similarly, I can take 3 to 4. That's it. And I don't take anything. Still it is subgraph. Understand? But don't ever draw an edge from 1 to 3 in this graph. If you draw it, that is not subgraph because that 1, 3 edge is not subset of the original graph, isn't it? So that's why these are all subgraphs. The concept is very easy. Let's see spanning subgraph of G. What is spanning subgraph of G is, let's say it is G dash, then the vertex set V dash should be equal to V, same vertex set, and edges should be subset or equal to E. Take all the vertices and subset of edges. See here, this is what spanning subgraph of the graph. Okay, so this graph is already subgraph and also spanning subgraph. So example, let me take a different graph 1 to 2, 2 to 3, 3 to 1, 1 to 4, let's say 4 to 3, 3 to 5. For this graph, Spanning subgraph is, for that necessary condition is what? The vertex set should be equal to V. That means take all the vertices first. That is important. But that is not compulsory in subgraphs, right? But in spanning subgraph, that is compulsory. It's must. Then let me take any subset of edges which are part of this graph. This is G. I'll take 3 to 5 and 3 to 1 and 2 to 3. That's it. This is spanning subgraph. You understand? So next, induced subgraph of GV comma E. What is induced subgraph is? So in that vertex set again V dash should be subset are equal to V as it is, like subgraph. But how it is different from subgraph then? Edge set E dash. So E dash is all the edges which are induced by which are induced in G. I will tell you what is the meaning of that. Let me write it. All the edges which are induced by vertices of V dash in graph G. So don't worry, I will explain you clearly what does it mean. So E dash is all the edges which are induced by this your vertices V dash in the original graph G. Example, this is your graph G. I am drawing induced subgraph. Okay. For induced subgraph, you have to take, I am drawing induced subgraph here. 1, 2, 3. It's up to me. Any number of vertices I can take because V dash should be subset are equal to V, right? So let me take 1, 2, 3, 4. So now I satisfied this condition. Now this one, you have to take all the edges which are induced by vertices 1, 2, 3, 4. So you tell me all the edges which are induced by 1, 2, 3, 4 here. 1 to 2 and 2 to 3 and 3 to 4 and 4 to 1. All the edges we should consider between this 1, 2, 3, 4 which are in G. So why I am not taking 2 to 4? Because it was not part of original graph G, isn't it? That's why this is called induced subgraph of this graph. One more example. Let me take only 1, 2, 5. Then what is induced subgraph? So take all 1 to 5 and look into this graph G and see all possible edges between 1 to 5. One is 1 to 2. Second one, what about 1 to 5? In original graph it is not there. Don't take it. Between 2 to 5 there is no such edge. That's why answer is this one. This is induced subgraph of this one with vertices 1 to 5. So these are the concepts of subgraphs. Okay, the simple subgraph, second one spanning subgraph, third one induced subgraph. Understand? Now we'll see one more concept called supergraph. Okay, supergraph is easy to understand after understanding subgraph. Example, let's say you have graph G and graph G dash. Okay, so whenever G dash is subset are equal to G, okay, we know what is subgraph, right? Whenever G dash is subgraph of G, then we say that G is supergraph of G dash. Okay, it's not different one. Whenever a graph G dash is subgraph of G, we say G is supergraph of G dash. Example, for here G dash is subgraph of this graph, right? Then we say G is supergraph of this one. Easily you can understand that. That means how to interpret supergraph? Supergraph is a bigger graph than otherwise equal to original graph, and it contains all the edges of your graph and more than that maybe, right? And some more vertices you can have. Example, if you have 4 vertices and few edges among them, for that graph, supergraph contains all that 1, 2, 3, 4 vertices and all that edges followed by some more edges and some more vertices. That's the idea about supergraph. It's very easy to understand, right? So now I would like to teach you what is connected graph with respect to this subgraph, supergraphs and paths, everything. Okay, let's begin with connected graph. What is connected graph? Connected graph is a graph GV comma E where there is a path between every 2 vertices. Connected graph is a graph where every 2 vertices are connected, otherwise there is a path between every 2 vertices. You know what is path, right? So using that easily you can understand. Example, see this one. This is connected graph. Why? According to the definition, I should show path between every 2 vertices. You see, 1, 2 there is a path, 1, 6 there is a path. some students get confused between path and edge. There is no edge between 1 and 6, correct? But there is a path from 1 to 6, isn't it? 1 to 2, 2 to 3, 3 to 6. Understand? So between every two vertices there is a path. You know what is path. If you don't know what is path, please go to previous lecture or previous video where I taught you path, right? Next, this one. This is not connected graph. Why? There is no path between 2 to 5. There is no path between 3 to 7 and so on, right? So this is about connectedness. So this is a connected graph but not this one. Now what is disconnected graph? Simple, a graph which is not connected. Since it is not connected graph, we say this as disconnected graph. Okay, disconnected. In that way, easily we can understand connected graphs and disconnected graphs. Let's see what is connected component. So connected component in the graph is a subgraph of that graph and which has some conditions. I will tell you that conditions. Whenever I say something is connected component for a given graph G, then condition number 1, it is a subgraph of the graph. Second one, it is connected graph. That means that component, whatever I am talking about, it is a connected graph. Third one, there is no supergraph of that connected component which is connected. We'll see one by one. Example, let's take 1 to 2, 2 to 3, 3 to 4 and 4 to 1. 5, 6, 7, 8. This entire thing is, let's say, one graph. Okay. In this graph, so this is called connected component. Why? I will tell you. Because it satisfies all the conditions. Condition number 1. For this entire graph, this part is subgraph. That's obvious, right? So definitely this is a subgraph. Correct? Second, it is connected graph. Yes, this subgraph. If you focus on C, this is C, then that C is connected, right? The reason every vertex is reachable from another vertex. You see 1 to 2 there is a path, 1 to 3, 2 to 4, everywhere there is a path. That's why it is connected. Third condition is there is no supergraph of C. In this entire graph, there is no supergraph of C which is connected. Example of one supergraph of C is 1, 2, 3, 4 and let me add one more vertex 5. Okay. So one more vertex 6. Okay. This is one super graph of your 1, 2, 3, 4, isn't it? This is what our target. This is our connected component C. For this connected component C or for this component C, this is a super graph. Okay, whatever you add here or anywhere, this super graph is not connected, right? That's why this condition is also satisfied. Anybody, can you show any bigger graph than C which is connected? Impossible. That's why this is called connected component. So some students think that 1 to 2, 2 to 4 is connected component. It is not. The reason, condition number 1, it's a subgraph of the overall graph G, right? This is your graph G. Yes, it is subgraph of your original graph G. Second one, it is connected graph. Yes, it is connected. Third one, there is no supergraph of C which is connected is absolutely wrong. I will show you one supergraph, that is 1 to 2, 1 to 4, 2 to 3, 3 to 4. You see this graph, example, let's say X, this is your C. Okay, then this X is supergraph of C, isn't it? Yes, X is supergraph of C or C is a subgraph of this X, but that X is connected, isn't it, in this original graph? That's why this 1 to 4 is not connected component. So finally, the connected component is one is this one, C1. So this entire thing. So what you have to look into for connected component is, so largest area I can say which is connected is one connected component. You see this entire maximally connected component, right? This means, so here all these vertices are maximally connected. Okay, if I extend it, then you may form a supergraph, but that will not be connected. That's why I can say this is one connected component, C2. So C2 is one connected component, C1 is one connected component in the graph. Okay. Now, if you have any doubt on any other components, then please check these three conditions. That component should be subgraph. This is a subgraph of the graph. Second one, it should be connected. Yes, it is connected, but there is no supergraph. That means there should not be any better graph than this one. Okay, that means by adding some more vertices to this, That means by extending this should not form connected graph. Then we say that this is connected component. Okay. One more example: 1 to 2, 3 to 4, 5 to 6, 7 to 8. How many connected components this graph has? See, this is maximally connected area, isn't it? Connected component 1 informally. This is connected component C2. Okay. If I extend this entire thing like one connected component, you are wrong. The reason, first of all, this entire thing is not connected graph, right? So that's why these two are separate connected components. 5, 6 is one more connected component, C3. 7, 8 is one more connected component. There are 4 connected components. Okay. So one important property here is when graph is connected, when graph is connected like this, definitely you can't see multiple connected components. You will see only one connected component, correct? So every connected graph has exactly one component. You should remember it. Okay. So this is about connected components. If graph is disconnected, then you will see multiple connected components. But there is one exception. That exceptions we'll discuss now. Okay. So what is exception is null graph. Generally null graph is supposed to be connected graph, but authors defined otherwise. In theory null graph is defined as disconnected graph. You should remember it. Okay. So there are a lot of theorems to prove them. If you keep null graph as, if you assume null graph as disconnected graph, then it will be very useful for us. Okay. So that's why this is only single graph, right? Only one graph. So that one graph, if I say it is disconnected, then that will be very helpful for us to prove theorems. Okay. That's why remember that null graph is disconnected graph. Now what about single vertex? For other graphs, simply follow the definition. Okay. When there is only one vertex in the graph, then graph is connected. Why? From 1 to 1 there is a path. Yes or no? There is only one vertex. Definition of connected graph is there is a path between every two vertices. Here there is only one vertex, then I have to prove that there is a path between 1 to 1. Recall trivial path. Yes, there is a trivial path from 1 to 1, isn't it? That's why this is a connected graph. But don't get confused when you have multiple vertices like this 1, 2, 3. Consider this graph 1, 2, 3 with no edges, then this is not connected graph. The reason, there is no path between 1 to 2. Understand? This is disconnected graph. So apart from null graph, every graph, to check whether it is connected or not, apply the definition. Okay. Don't apply the definition for null graph. Okay. Simply say that the definition is only for graphs with with number of vertices greater than or equal to 1. If number of vertices are 0, then it will form null graph, and null graph is disconnected graph. Understand? So this is the story about null graph. Now observation. Whenever you have a graph which is connected, then the number of connected components are definitely 1. If your graph has, if your graph is disconnected like this, example 1 to 3, 4, 5 to 6, 7 to 8, 9 to 10, then the number of connected components will be more than 1. So here number of connected components are 1, 2, 3, 4, right? 4. So finally, but be careful with null graph. Number of connected components in null graph is, there is no component, right? So that's why 0. Okay, 0. Apart from null graph, any disconnected graph if you take, then definitely you will see, more than one connected component. Okay, so more than one connected component. Now, let's classify the number of connected components like this: 0. Okay, if your graph has 0 components, 1 components, and more than 1 components, then what can we conclude about it? We'll see. If number of connected components are 0, then it is null graph, which is disconnected graph, definitely. If number of connected components is 1, then definitely it is connected graph. If the number of connected components are more than 1, definitely you can say that the graph is disconnected. Okay, so this is the story about connected components. Let's see operations on graphs. Let's say I have two graphs G1, G2, and G1 is V comma E1, G2 is V comma E2. That means two graphs are on same set V. Vertex set is same and edge sets might be different. So then I can define union, intersection, minus generally. Okay. So I can define union, intersection, minus for different vertex sets also, but most of the time we are interested in these operations for graphs with same vertex set. So assume that let's say vertex set is same. Then how I can define a union, we'll see. So we say that is G1 union G2. So whenever I define a graph, I should define what is vertex set, what is edge set, isn't it? So here I define what is my new vertex set. Okay, that is just same vertex set as G1s and G2s. So V, and edge set is E1 union E2. That means take all the edges of E1, take all the edges of E2 and union them. That means if you have an edge twice, then example, you have an edge in G1, same edge in G2, then take only one time. That's why I have written union operation. Okay, so here assume that all these graphs are simple graphs. Okay, I'm talking about simple graphs specially. Let's define these things for simple graphs. That means no parallel edges. So we'll see with example. Example, I have a graph 1 to 2, 2 to 3, 3 to 4 like this. This is G1. Let's take G2 with same vertex at 1, 2, 3, 4. That is what I defined. Then 1 to 4, let's say 4 to 3. I am randomly taking these edges like this. Then what is G1 union G2? So G1 union G2 is take again same vertex set 1, 2, 3, 4 and draw all the edges of G1, all the edges of G2. So it will be 1 to 2, 2 to 3, 3 to 4 and add all the edges of G2. 1 to 3, since already 1 to 4, since already 4 to 3 is added, don't add one more because we are doing union, especially I am defining simple graphs. Okay. So this is the result of union operation. This is a new graph. Vertex set is same, but edge set is union of previous two edge sets. Now we'll see intersection, G1 intersection G2. What is G1 intersection G2 for these two graphs? It is defined like this: vertex set same and edge set is nothing but E1 intersection E2. So G1 intersection G2 is again a graph with vertex set V and edge set is E1 intersection E2. That means take just common edges of both graphs. Let's do it. 1, 2, 3, 4. This is G1 intersection G2. Tell me what are all the common edges in G1 comma G2. One is 2 to 3. Second one, anything else? 3 to 4. That's it, right? So that's why this is G1 intersection G2. In that way, easily we can understand about G1 intersection G2. Let's see minus operation. So G1 minus G2 is nothing but vertex set same, but you have to take edges of E1 which are not in E2. This is set operation, minus operation, right? All the edges of E1 which are not in E2. That is what the concept of minus. Let's do that. I am drawing G1 minus G2 graph for this G1 G2. First take same vertex set as mentioned in the definition 1, 2, 4, 3 and all the edges of E1 which are not in E2. That means this is all the edges of E1. These are all edges of E2. 1 to 2 is there in G1 but not in G2. Add it. Next 2 to 3 it's there in both, then don't add it. 3 to 4 it's there in both, don't add it. That's it. And some students do this mistake that they add 1 to 4 and they say that it is not there in G1. But E1 minus E2 is all the edges of E1 which are not in E2. It's not like all the edges of E2 which are not in E1. That is what you are going to do, right? If you want to do mistake, you do that. But the correct thing is all the edges of G1 which are not in G2. Then only 1 comma 2 comes into the picture. So this is about minus operation, right? So every operation between these graphs is giving you new graph, right? So G1 union G2, G1 intersection G2, G1 minus G2, right? So now we'll see what is complement of a graph. This is one more operation. It's a unary operation, I can say. When you have a graph G, then we can define G bar. So G bar is defined like this. G bar is V dash and E dash. Oh, new vertex set, new edge set. What is V dash? V dash is V. That means same old vertex set, and edge set E dash equal to edges of complete graph minus edges of the graph G. So here you have to take edges of complete graph. We know that in a complete graph between every two vertices there is an edge. Okay. So that means, so I can say that from all the edges of the complete graph, remove edges of this G, then you get edges of G bar. That's it. Example, let me take like this 1, 2, 3, 4, and let's say 1 to 3, 2 to 5. For this graph, what is G bar? G and G bar. How I draw G bar is vertex set same, right? Then I write 1, 2, 3, 4, 5. And we have to apply minus operation between what? All the edges of complete graph which are not in E. Okay, so you can do this thing in two ways. One, first draw the complete graph with 5 vertices. 1, 2, 5, 4, 3. Okay, so here Kn, n is what? Number of vertices in your graph G. Since you have 5 vertices, here n value we should take as 5. That means we have to construct K5 first. Let's do it. 1 to 2, 2 to 5, 2 to 3. What is complete graph? Complete graph is a graph where between every two vertices there is an edge. 1 to 4, 4 to 3, 1 to 3, 2 to 4, no 3 to 5, 1 to 5. Wherever you can, please add it. Between 4 to 5. Did I miss anything? So from 1, let me check it. So every vertex degree should be 4 because there are 5 vertices. Really, if you add edge from every vertex to all other vertices, then every vertex will get remaining, I mean 4 edges, isn't it? Example here 1, 2, 3, 4. Yes, for 4 1, 2, 3, 4. For 3 1, 2, 3, 4. For 2 1, 2, 3, 4. In that way 5 1, 2, 3, 4. Yes, it's a complete graph. Between every two vertices there is a edge. Now what is this G bar is, take edges of complete graph. Yes, I have taken, and remove edges of E. This is edges of E. This is all these edges are E here. Example, that means you have to draw an edge which is in this but not in this. Example 1 to 4. So easily you can understand that this graph contains definitely edges between every two vertices. Then whenever there is no edge in your original graph G, definitely that should be added. 1 4, you see. Next 3 4, but it's there here also, then don't add it. That is what minus operation. Any special edge you have 3 5, but it's not there here, then you add it. That is what we should do. Next 2 5 2 5, don't add it. 2 4 2 4, no, there is no 2 4, right? Then you can add in that way. Anything else? 1 3 1 3, don't add it. So easily we can understand that there are 10 edges here. If you count, out of them 1 2 3 4 5 edges are part of this graph, then you get 5 edges here, only you got 3. 10 minus 5. So which one is missing is, we'll see. What about 3 to 5? It's drawn. 1 to 3, yes, you see 1 to 3, it's there here and it's there here, don't draw it. 4 to 2, yes, we have added. What about 4 to 3? It's already there. Yeah, between 4 to 5. Between 4 to 5 you have an edge, but here there is no edge, then you add it. That is what we should do. Correct? So 1 2 3 4. One more edge we should get, right? So this is our imaginary edge, right? 1 4. Next. Now 1 2 3 4 5. Between 3 5 we have drawn. Between 2 4 we have drawn. Between 1 4 we have drawn. Between 4 5 we have not drawn. See, between 4 5 you have an edge. Yeah, just now we have drawn. Then 1 2 3 4. So here 1 2 3 4 5. So there is one more edge in this graph. We have to add it. The reason it's not there here. What is that? Guess it. Stop the video here and think about that edge and try to find out it. So is it 1 2? No. Is it 1 3? No. Is it 2 4? But it's already drawn. Is it 2 3? No. Is it 1 5? Yes, you see, between 1 to 5 there is no edge here, but it is here. That is what the complete operation, that is the way that operation works. What is it? Edges of complete graph 1 5, but not in E. Yes, but not in E. That's why we have to add it. So these are the 6 edges. In that way always we can construct G bar. So rather than doing this one, I would like to tell you one easy idea that, however, complete graph contains all possible edges. So no need of checking whether some edge is there or not. Directly, this formula says that take all the edges of complete graph which are not in E. Then directly you see any edge which is not in E, that definitely will be there in complete graph. Then no need of checking whether it is present in original complete graph or not. Directly you do like this, between 1 4 there is no edge here, then you add it, then quickly we can do the things. Okay, so we'll take one more example and we try to calculate G bar, this time without constructing complete graph. Directly we do that. 1 2 3 4. Let's take this one. For this graph G, what is G bar? Okay, I don't draw complete graph, without that even I can do it. Okay, now between 1 3 there is no edge, then definitely this edge is there in complete graph, and it is not there here, then you add it, right? So that is what this operation. Next, 2 to 4. Anything else? No. This is the way we can easily draw complement graph of any graph. Okay, let's solve some problems related to connectivity. Problem number 1, a simple graph has 10 vertices and 25 edges. Then the number of edges in complement graph. So before solving this problem, I would like to give some details about G and G bar with one example. Example, this is your graph G. Okay, then let's say this is G bar. So you know what is G bar, right? G bar contains same vertices 1 2 3 4 and all the edges of G bar which are not in G, correct? So which are not in G means between 1 to 4 we draw, and between 1 to 3 we draw, and between 4 to 2 we draw. Generally we define this complement concept to simple graphs. Okay, my assumption is, let's say graphs are simple. Then you can easily observe one thing, whenever there is no edge you are drawing it, then all the edges of complete graph definitely will be present either here or here, because if it some edge is not present between any two vertices, then definitely you are drawing here. Any edge is not present here, the only reason is it is part of G. Then what I want to say is, if you do G union G bar, then you get all possible edges a graph can have. That is complete graph, isn't it? So maximum number of edges a graph can have is like complete graph. That's why if I do G union G bar, we are collecting all the edges possible. That's why it will form complete graph, isn't it? So easily we can observe it. We never miss any edge. Second one, G intersection G bar. Since whenever there is edge in G, we are not drawing it. Whenever there is no edge, we are drawing it. Then there is no common between these two graphs, right? G intersection G bar is empty graph, I can say. Okay, let's denote by empty set. So my intention is it is empty graph. So keep these things in mind. Then the question is the number of edges in its complement. What I can observe is number of edges in G plus number of edges in G bar, because G union G bar is K. Then if I add number of edges in G and number of edges in G bar, since there is no duplicates, then you get what you see, number of edges in G plus number of edges in G bar according to some rule. Then you get all possible edges in a complete graph, that is number of edges in complete graph, where n is nothing but number of vertices in G comma G bar, right? So let's do it. Number of edges in your graph G, how many? 25, plus number of edges in G bar x, we don't know, equal to number of edges in complete graph with n vertices, where n is nothing but number of vertices of G, which is given as 10, n value 10, k10. How many edges a complete graph contains? So we know the formula for it, right? N into n minus 1 by 2. So that is nothing but 10 into 9 by 2, which is nothing but 45. So here 45. So 25 plus x equal to 45, then x value should be 45 minus 25, isn't it? So that is 20. In that way you can solve this problem. Let's see one more problem, which is a theorem actually. So whenever I solve or whenever I prove a theorem, it improves your understanding. That's why generally I suggest you to prove some of the theorems. So here I help you to prove this theorem. Whenever I claim a statement while doing proof, then stop the video and think about that claims. Like example, if I suddenly say some statement, you don't understand that. When you don't understand, stop the video and think about that statement. Once you understand that statement thoroughly, come back to the video and continue the video. Okay, so in entire graph theory you will do that. Okay, start. Problem number 2. If a graph contains at least 6 vertices, then either such graph G or G bar contains a triangle. Why? First question you should ask yourself is why. Okay, so think about it. If you cannot understand this, then watch the video first. Since there are 6 vertices, I say them as A, B, C, D, E, F, let's say. But there are some more vertices, right? In the theorem, it is said that at least 6 vertices. But I am taking only 6. But still there are some other vertices. I don't want to consider them. Now, this is your G. This is your G bar. In G bar also you have A, B, C, D, E, F, isn't it? Okay. Now, the statement, we have to prove that either G or G bar contains a triangle. Triangle is nothing but a triplet of vertices. That means there will be 3 vertices which are mutually adjacent like this. Then we say it's a triangle in graph theory. Okay, why there is a triangle I will tell you. Let me take a random vertex called A and I want to talk about this A now. Such vertex A will definitely have adjacency with at least 3 vertices either in graph G or G bar. That is my statement number 1. If you don't understand that, stop the video and think about it. What is that statement is? See, this vertex A random vertex, is definitely adjacent to at least 3 vertices. Why? I am not saying that it is in G. I am not saying that it is in G bar, but either in G or G bar definitely it happens. Why? Because if it won't happen here, that means if A is not adjacent to 3 vertices here, let's say B, C, D, okay, then definitely A will be adjacent to B, C, D here. Example, you can, this is called proof by contradiction. You can argue like this, sir, let's say my, you know, vertex A is not at all adjacent to anyone. What you said is A is adjacent to at least 3 vertices you said na, but let's say A is not adjacent to anything, then how can you justify? I said A is adjacent to at least 3 vertices either in G or G bar. If in G A is not connected to anything or A is not adjacent to anything, then definitely in G bar there will be edge from A to B, A to C, A to D, A to E, A to F, so that A is adjacent to more than 3 vertices. Okay. Second one, what if you have only 2 edges like this, and if it is not connected to these 3, then definitely in G bar A will be adjacent to these 3 in that way. So easily we can understand that your vertex A, which is a random vertex I am talking about, that will be adjacent to at least 3 vertices either in G, otherwise G bar. We can't stop. Let's say that is adjacent, okay, to 3 vertices in G. I am fixing it. If you want to say that it is G bar, that's okay. Then we can argue with the same logic. Okay. I assume that, let's say in G that is happening. What is that? A is adjacent to 3 vertices. Now, the remaining thing, this is for sure, right? You agree? Then, what I want to say is, such vertices are, let's say B comma C comma D. Let's name them. Now, if I prove that if there is an edge between B comma C, then game is over, right? Then I can see the triangle and I can stop the theorem. I can say that theorem is completed because proof is done. But you should argue that, how can you guarantee, sir? How can you guarantee this edge, sir? I cannot guarantee. But what if there is edge between C to D? Still it forms a triangle. Then you should ask that, sir, how can you guarantee it? I cannot guarantee. What about, if you have edge between B to D? Still it forms triangle. Then still I win. But again you can ask, sir, how can you guarantee? Correct? Yes, I cannot guarantee. But let's say between B to C, C to D, so I am focusing on BCD and graph G. Between BCD, between BC if there is edge, or CD there is edge, or BD there is edge, definitely it forms triangle here. Then I want to say that, let's say there is a triangle. If example, you want to say that there is no triangle in G, then what is the opposite statement you should take? Let's say play this kind of game. I am proving that there is a triangle here. You are proving that there is no triangle. Then what should be your take? You should say that, sir, there is no edge between BC, there is no edge between CD, there is no edge between BD. Why? If there is edge between BD, it forms a triangle and I win. Okay. In entire discrete maths, then whenever there are theorems, we prove theorems using a concept like this. I am one player, you are another player, we are playing a game. I take one stand, you take opposite stand. Okay. And end of the day, someone will win. Okay. So whoever wins, their stand will be the correct statement. Here my stand is between BC or CD or BD, there is at least one edge. Then your stand should be there is no edge between BC, there is no edge between CD, there is no edge between BD. Keep that in mind. That is your stand. Okay. Then really if your stand is correct, then what is your stand? There is no edge between BC, no edge between CD, there is no edge between BD. Then come back to G bar. Then observe BCD in this G bar. You said there is no edge between BC in G, right? Then there will be edge between BC, there will be edge between CD. Concept of G bar. There will be edge between BD. It forms a triangle here. Maybe you are winning here. Yes, I cannot show triangle here. But whenever I cannot show triangle here, automatically they are forming triangle here. Understand my point? So that's why definitely either here or here there will be a triangle, otherwise three vertices which are mutually adjacent. Let me revise that theorem again. First what I did is I proved that I have taken one random vertex and I proved that it is adjacent to at least three vertices either in G or G bar. Then you agreed that, correct? If you don't agree, stop the video and think about it. So why that statement is correct? Once you agree that, then what I said is at least either BC or CD or BD will be connected. Then you did not agree. Okay. If you agree that BC or CD or BD are connected, then it forms triangle and I win. Theorem will be completed. Then if you don't agree that BCD are not connected or adjacent, if BCD are not adjacent, none of them are adjacent to anything, then in G bar all these will be like BCD, no one is adjacent here, then here they will be adjacent, right? That's the concept of G bar. Whenever there is no edge here, we should draw edge here, correct? If I do that, then BCD will form a triangle. Still you want to win, then you say, sir, there is no edge between BD. Okay, then there will be edge here between BD, it forms a triangle. Understand that? So in any case, then we can say that there is a triangle in either G or G bar. For that, 6 vertices are compulsory. If you give only 5 vertices, I can't prove it. The reason I can't take the first statement. What was the first statement? I said there is a vertex A which is adjacent to 3. Need not be. Why? Because this may be possible like this. When there are 5 vertices, then A, B, C, D, E, then A may be adjacent to B comma C here. The same A is adjacent to D, E here, let's say. Okay, then what was my first statement? My first statement was there is a vertex A which is adjacent to at least 3 vertices is not true when there are 5 vertices. But if there are 6 vertices, then I can take that statement and I can prove the remaining theorem. So finally this theorem is correct.